matrix, or we call it transition matrix. So how do we form this matrix? If you look at the row, this is a row, right? This is column, right? The row, we are having the fixed channel input. So I am sending x naught. What is the property of getting y naught, y1, yk minus 1, right? Because there are k number of y's, so there are k number of y's, right? And then there's j number of x. So the
yes, transition matrix, is it also the same one they use for the Derby algorithm?
I think we'll come to that in the channel decoding, yes. Right, so this is, you all learned before? We will find out on Wednesday. Alright, so just take it as this. So if you look at this vertical columns, right? It is fixed output, fixed channel output. I'm getting y, depending on what's being sent, right? So this, if you write down the entire combination, you have a matrix. Right, so the fundamental of the channel matrix, I think this is a summation of all the one in the, for all j, right? So let's say for a fixed j, is the sum of all the members in the row, right? So if I add this plus this plus this, the total is equal to 1, right? Which makes sense, right? So if I send out a symbol xj, all the possibility of different y that I receive, if I add up the probability, it will be equal to 1. Okay, so let's revise this again. What this actually means is that this is a joint probability distribution functions, right? So this is the probability where xj is sent and yk is received. So you will see that it's different from just y. So it's not equals to yk bar xj, right? Because this probability is a conditional property. The condition is that xj is being sent. So the joint probability distribution where xj is the symbol being sent and yk is the symbol being received, and this is equal to this, right? Remember you learned this in probability? Remember this?
Give back.
Right. It makes sense, right? Because this is just the probability of getting yk. If you set xj, right? But you need to multiply the probability of xj being sent, right? So you multiply the two together, you get the probability of xj being sent, yk being received. Right? So let's look at another thing. So the probability of yk, right? So what is the probability of yk? It's just equal summation of all the whatever inputs that you have, you possibly have, right? All the combination of all the jk, right? Right? Do you understand this?
I think I keep back.
Right, probability of yk being received is equal to the probability of all this added together. Right, so if you look at the matrix, so if I add the horizontal axis, it must be equal to 1, right? If I add all the columns, the members in column, what do I get?
1.
I get probability of y naught, right? In this case, right? That's what this summation means, right? Is that what the summation? No. Summation doesn't mean just that. Sorry, I need to correct myself. But it's related to that, right? Because you need to multiply by the probability of PG, right? So I was wrong. So don't quote me, right? So this is not there. So if you're recording, so it's wrong. Okay, basically it's just what this is, right? So because you need to really multiplied by the probability of xj being sent as well, right? So this is all the probability that you will get yk out. Okay, so let's use a simple example to illustrate what we're trying to do, right? So this is a binary symmetric channel. So binary symmetric channel meaning binary means that there are two input and two output. So the j is equals to k equals to k. Right, this is a binary. This is what it means by binary, meaning that there's only two numbers here, 0 and 1, and this is 0 and 1. Why is symmetry? Symmetry is that the probability of having the wrong symbol being received is p, right? There's an equal chance of 0 being received as 1. It's the same as the probability of 1 being received as 0. Right, so this is how you draw this transition probability diagram. Okay, so this is called transition probability diagram. Right, so if this is the probability of getting an error, and then 1 minus p is the probability of 0 being sent and 0 being received. Okay, so this is an example of where a special case j equals to k equals 0. Okay, a lot of definition over here. Right, so remember entropy of our source. When we say entropy of our source, we are looking at the average information being sent per cohort, right? But in this case, we are actually measuring the prior uncertainty about x. Okay, what do I mean by that? Let's go through the example. I mean, go through what is being shown over here. Right, so let's say, okay, this is actually just a stylistic way of writing x. This is x. So x is a set, right? So this is an x. I don't know how to write the x in a very stylish way. X is a set where you have all the x naught up to x. X is the one that is j, the big J minus 1, right? And then y is the set where you have very stylish y is the set of all the y not up to the y k minus 1. Right, so this is the x and this is y. Right, so let's take a look at what the definition is. The conditional entropy of x is given by this, right? So x, okay, what it means is that, so I have yk received, right? I'm receiving yk, right? If you look at this, what do you understand this is? So this is, do you remember what is this?
Entropy.
The log 2.
Amount of information.
Yes, the amount of information that you have. Right, the more information you have, it means the more uncertain, right? The more uncertainty it was before, right? The more uncertain it was before means that more information I have, because this is a log base 2 1 over p, right? So if it's uncertain, means that there is some, I wouldn't know what is the probability is not so high, also not so low, right? There's an uncertainty. So there's some, so it's really a measure about uncertainty in this sense, right? okay, if you look at this, what does it actually measure? The probability of xj dash yk. Right, so what does it mean? So yk is being received on the output, right? So we know, because we are at the receiver, we receive the symbol yk, right? So that probability is, what is the probability of it being xj if I know I receive yk? What is the probability of xj is being transmitted if I know yk is being received?
I remember last time it says it's just it's like direct piece, right?
Yeah.
In
Yes.
English, it's what's the probability of A happening given that B has happened.
Yes, correct.
So is it the same thing?
Yes, yes,
What's the
it's the
probability
same.
of X
So-
transmitting given
So what's the
Y
probability of
transmitting?
xj being transmitted when I receive yk?
How I know?
It's like calculating.
because you don't know how many X term there is inside.
Yeah,
Yeah.
later we will give you a very simple.
Quite interesting, like,
We'll
imagine
use a
the
simple example of the
Oh, I don't like
binary
sia.
symmetric.
Very interesting. I'm not sure
So-
you
so-
that the person sent
so
what you really want to hear.
what is important is to understand what's the probability. What does it represent now,
Guess.
right? Because in communication, I want to know when I receive 1 or when I receive 0, what's the probability of actually transmitting 1, right? When I receive 1, right?
Oh, so it's the actual and the receive part that
Right.
might be tilting noise that kind.
Like how sure are you that the person sent
The
what they
information
sent?
is true. Oh,
Yeah. Okay. So
True input.
So, and then you need to multiply by the probability of this actually happening. So if you sum it up, this is what is it? So what is the meaning of this? If you sum this up, you remember we sum the probability multiplied by the expected. So when you sum everything up, it gives you kind of a measure of how what's the
Noise?
no
Unpredictable.
what's the uncertainty that you have when you receive a certain bit, right? When I receive this symbol yk,
It's actually the
yeah, what is the actual
input to be transmitted by
yeah,
the
what is the
antenna.
kind of uncertainty I have when I receive this? Okay, so this is what it means.
Oh, what's the
So if you look at this, the conditional entropy of x given that y is equal to yk. So it is actually a measure of the prior uncertainty about x given that y is equal to yk.
Prof, can I clarify the summation over J part?
Uh-huh.
When you put that summation over J, you are doing it for every single Y you receive, is
No,
it?
no.
XJ.
Every single xj.
Oh, every, yeah.
Because you receive yk.
Yeah.
Yk is fixed. You already receive a particular yk.
Also, you're just using one
Yes.
thing that you receive to make a deduction about
Yes.
everything that they said.
Yeah. Okay. And then you further generalize. So just now what we described over here is just only one yk, right? So if you further do up the entire thing, so this is just summing up for only one single yk. So you do the entire thing, this is what we call the conditional entropy. So this is kind of summing up. If I receive y, any yk, what is the probability of what is the actual thing that's being sent out, right? Don't worry about this now. Later we'll show an example just using 2D. Okay. So let's. The example is quite long. Let's just accept it for the time being that this is how it's being calculated, right? So I think the summation, the double summation is fine. Okay? Because it's just this, but then now I'm receiving over the entire y, right? So I just need to add up all the effects. Okay? So I just add up in the entire y. Right, so this entropy Hx represents the uncertainty about the channel input before observing the channel output. Right, so remember what is this? Okay, this should be capital letter. Okay, how to calculate this? Do you remember how to calculate H? Based on what we know just now. How do you calculate it? It's the probability of, it's the summation. Okay, let me get the summation sign. Summation, right? There's a summation. It doesn't show all the way. Summation of the probability of K is the, is it K? No,
Yeah.
we use J,
Oh,
sorry. We use J for X. Small letter J. This is not, because we are submitting, we are we are adding up all the Xj where J is equals to 0 up to J is equals to big J minus 1, right? Right? And then this log base 2 1 over Xj. Right?
Oh, it's 1 over P Xj, isn't it?
Ah, sorry. Yes. Not 1 over Xj. 1 over the probability of Xj. Yes. Okay. I think when I write it down like this, it's easier to understand what is calculating, because you have all the different Xj, and all the different Xj's have different probability, right? Right? Some has high probability, some have low probability. And when you do this summation, what you get is kind of the average uncertainty, or the uncertainty about the channel input. Right? Because this is what it is kind of measuring. So each x bar y, right, is a conditional entropy, represent the uncertainty about the channel input after you observe the channel output. Right? Then the difference of this is the uncertainty that is resolved after observing the channel output. So obviously after you observe the output, you will have less uncertainty, right? About what the input was. Right, so it represents the uncertainty that's resolved by observing the channel output, but it's not 100% resolved, because there's still like even if I send a certain you receive a certain symbol y, it doesn't mean that there's 100% the x is being sent, right? But it definitely resolves some uncertainty, and this is what we call the mutual information of the channel. So you can again think of it. First of all, I don't know. So you are thinking from the receiver end of view. There's a probability distribution of what x will be sent to me. Then I receive y, right? So now after I receive y, after I receive all the output through the channel, I have less uncertainty on what I know should be the input. Right? So this difference or the uncertainty being resolved is what we call, is a definition of mutual information of the channel, right? So, okay, I hate the symbol being used here, but it's the y and the x. These are just x and y, but in a very stylistic way, right? So don't worry, it is, sometimes x is just representing all the sets of the inputs. Right, so it is symmetry, kind of understandable, right? Symmetry means that because it's the channel, it shouldn't have any directionality, right? So I send to you, you send to me. It has the same. It should have the same kind of property, right? It's symmetry, right? So it is non-negative. It shouldn't be negative, right? Because after I receive the output, I shouldn't. My information I know about the input should be more than that, right? Alright, so a counter example is that after I look at your midterm, I thought I know you very well. Then after I look at midterm result, I thought that I probably don't know you at all. So that's a counter example where it becomes negative. But normally, if I have more information, I have information output, then I should know you better, right? I should know what was being said better. So it should be positive. It should always be non-negative. Non-negative means that it can be zero, of course. You cannot lose information by observing the output of the channel.
But that's assuming that the output is so-called the true information set, right? Because there may be some, it's just that you don't know, right? Your observe is not.
I mean, that's why the limit is zero. Means if there's really error that
you see nothing,
what I receive is random, then of course I don't know anything.
Oh, okay.
Right? So there's a number.
So zero is C now.
But it cannot be worse.
Means I have to give information to see the information.
Okay, this one.
Oh, it just means you cannot look at it and have dementia and forget some shit. That's what it means.
Okay, this one actually can be proven mathematically. It's not. If you look at how this is being defined, this is defined as right h minus h. Alright, so this is being defined as h x minus h x bar y, right? So you can probably see that you can show this to be true, because this is when x and y is being so this can be shown, okay, but let's take a look at the results. So h is the uncertainty, the average uncertainty associated with h. Hy is the same thing for y, and then minus this. This is just a different way of writing the probability, right? So there's nothing surprise. So the mutual information of channel is related to the joint entropy of the channel input and channel output like this. So you see there's actually a lot of symmetry, right? So x and y can be swapped, and then you will see a difference. Okay. So far so good. Alright, so now let's come to what we mean by channel capacity. Alright, so in this channel capacity, the units is bits per channel use, or bits per transmission. Right? So what this is, so this is the maximum of all the possible I, right? And all the possible I, what are you changing? You are changing all the possible input probability distribution of x. Meaning that there are, so xj can have a, so we have x, right? X is consists of x naught, x1, x2 up to xj minus 1, right? So each of this will have a probability distribution, right? So it has a probability distribution. And all so the channel capacity, because it's just stated that is the maximum of, so depending on how this x, the probability of x is being distributed, doesn't matter, but I just want to find out what is the maximum value. So depending on how x naught is, so for example, give you a concrete example, maybe there's 0.1 and then 0.2 and then so on, right? But then there's also another distribution, maybe this is 0.01 and then this is 0.5 and so on, right? So all the possible distribution, probability distribution of x can be there, and then you calculate, you get the maximum mutual information. And this maximum mutual information is the channel capacity, and the units is bits per channel use, right? So this is very precise. It's still not what we understand by bits per second, right? So this is not our channel capacity by bits per second. This is not. Right? This is bits per channel use. Of course, in general, finding this is very challenging, and it may not be fruitful at all. But this is the theoretical basis. I think we are not okay. I've uploaded a PDF copy of this famous Shannon paper. It's a master's thesis in MIT. It's always kind of viewed as the best master's thesis MIT ever produced, because it has been used in communication and in so many other parts, how we do communication. So, okay, anyway, let's use a concrete example. The simplest example that you can find is a binary symmetric channel, right? Where j equals to 2, k equals to 2, and it's symmetric, meaning the p is the same probability that 0 is being read as 1, and 1 is being read as 0, right? So there's a possible that error will happen in this channel, right? And then and the probability, when we write them down, the probability of getting y naught as output when x1 is being sent is the same as this, right? So when you learn conditional probability, you see that this is a property of conditional probability as well. Have you seen that? Do you remember? Okay, for this, I think there's a condition for this to be true. I can't remember. What's the condition for this to be true? That this is equal as that. Sorry? Yeah, I think it's independent, right? They are both independent, right? Okay, so okay, let's assume that this is true. So my probability of receiving, because this is a symmetric channel, right? So my probability of receiving y naught when x1 is being sent is the same as my probability of getting y1 when x naught is being sent, right? So this is equals to p, right? So this is what we mean by symmetric channel, right? So this arrow over here, this p, this is p, okay? And then the probability that the correct symbol is being sent across is 1 minus p, okay? Alright? Okay, so far so good. So we have written down. So we can write down the channel capacity as such. You want to practice why there's such a big jump from here to here. So what is the capacity? Is the mutual
xj
y, right?
yeah.
Remember?
Semicolon.
Sorry, it's a semicolon. Alright, so how is it defined? It's defined by this. Or it's defined by this. Right? We can write this down. I think it's good to convince ourselves instead of just accepting the value, because this is easy to derive. Right? Let's xy minus h x y. What is this? We do this together
Summation.
and not rely on me.
Summation.
Okay. What is this?
Summation. And entropy of x.
What is this?
Summation j
Which is what?
px.
Let's say because this is a binary symmetrical channel, right? It means that the probability of getting 0 and 1 are the same, right? So if that's the case, remember what was it? It's actually 1, right? Actually the answer is 1 for this.